Hello and welcome back to Complex Analysis. And you might already know, first as always I want to thank all the nice people that support this channel on Steady, via PayPal or by other means. Now finally in today's part 6 we will talk about the Cauchy-Riemann equations. In order to understand them, we first have to recall the two notions of differentiability we have for a complex function. The first is the normal one, the one we introduced at the start of this series. This one we simply called complex differentiable at a given point z0. Now, as a reminder, in other videos I already explained, the domain here doesn't have to be the whole complex plane C. It's sufficient to have an open subset. However, this might be distracting in this video here, therefore I always write C for the domain. So if needed, you can just substitute this domain with any open subset U. Okay, back to the differentiability here. This one can be described as a linear approximation in C. More precisely, this means that we can find a complex number we can call f prime of z0. Indeed, this could be any complex number. Then, with this, it's possible for us to write f of z as a linear term plus an error term. And you already know, everything happens locally around z0, therefore the constant term is f of z0. Then, next comes the linear map, which has a slope given by f prime of z0. More precisely, we have this number times z minus z0. So you see again, this is the linear approximation of the function f around the point z0. And please recall, in real analysis, this represents the tangent. Therefore, the only thing missing here is a corresponding error term we could call phi. Of course, this phi is also a function from C to C. Now, as an error function, this map here should go to 0 when we send z to z0. And this convergence to 0 should go faster to 0 than a linear function would do. Or more concretely, phi of z divided by z minus z0 should still go to 0 when we send z to z0. Now, with this property, we really get a linear approximation around the point z0. Indeed, this is what we could read as the definition for complex differentiability at the point z0. However, to be honest, it looks a little bit different than the definition we gave before. Yet, I would say it's not hard at all to get this reformulation from our definition. And I guess it's a good exercise for you to think about it. After this, you see, we simply can take this for the definition of complex differentiability. And that's a good thing because we can nicely compare this to the definition of total differentiability we explained in the last video. As a reminder, this definition we introduced for functions from R2 into R2. And there, please recall, we have a one-to-one correspondence between functions from C to C and functions from R2 into R2. Therefore, often both functions are just called by the same name f. However, to distinguish them, I give the last one here an index r. Okay, now we can recall the definition of total differentiability for such functions. Also there, we have to fix a point in the plane, so let's call it x0, y0. Then we know the function is called totally differentiable at this point if there exists a matrix J and an error map phi. Please note, I use another variant to denote the letter phi here. Then what we need is also a linear approximation, now given by this matrix J. And lastly, of course, this error term here should also go to 0 in the same way as before. Which means if we divide it by the length of the difference vector, we still get out 0 in this limit. Here please note, before this 0 was the 0 in the complex numbers, and now this 0 is the 0 vector in R2. However, using the identification C with R2, you could say they are exactly the same. Therefore, a natural question here would be, where exactly is the difference between both notions here? So I would say, let's try to spot all the differences. First, this might be obvious. In the second case, we see when we use the division here, we need the length of the vector. This is what you know, we can't divide vectors. However, in the complex numbers, we don't have this problem. We simply can divide one complex number by another one. Now, maybe this is not a crucial difference because both things just explain that the error term goes to 0. And of course, if we wanted, we also could use the absolute value here. Indeed, this wouldn't change anything for the linear approximation here. Therefore, we have to look at the linear approximations to see the differences. Since we immediately see that the constant terms fit, we look at the linear terms here. And there you see, this dot here stands for the multiplication in the complex number c. And that's the difference because this multiplication does not exist here. Indeed, what we find here is a matrix vector multiplication. Now, exactly this does not translate in general to the multiplication in C. Therefore, the conclusion is immediately this definition here, complex differentiability, is much stricter than this definition there. And now, in order to get a translation from the complex definition to the one in R2, we have to answer one question. Namely, in which cases does a matrix vector multiplication represent a multiplication in the complex numbers? Now, because we know how to calculate with complex numbers, we can answer this question without any problem. Just let's check how the multiplication in the complex numbers looks like. So we take two complex numbers, w and z, and multiply them. Of course here, w and z have a real part and an imaginary part respectively. Therefore we say w is equal to a plus ib and z is equal to x plus iy. And now we just do the multiplication where we use that I squared is minus 1. Then we get a times x minus b times y plus the imaginary part, which is b times x plus a times y. Of course, this was not hard at all because you know how to calculate with complex numbers. However, now we want to rewrite this as a matrix vector multiplication. And the vector should represent the complex number z, which means we have x and y as the coordinates. And on the left of it, we have a 2 times 2 matrix where the numbers a and b should occur. And indeed, how the entries exactly look like, we have to figure out now. And of course, this is no problem for us because we already know the result. The first component should just be the real part here. And then the second component is just the imaginary part. And now the question is, which 2 times 2 matrix brings us to this result? Now the first row we see immediately because it should be a and minus b. Of course, in the same way, we also see the second row, which should be b and a. And indeed, that's it. This is the matrix that represents the multiplication of complex numbers. Therefore, our conclusion here is, if we want complex differentiability, we need that the Jacobian matrix here has this form. So I would say, let's fix this important result with a theorem. In fact, in this theorem, we will now find the Cauchy-Riemann equations. Okay, in order to get everything together, let's start with a complex function that should be complex differentiable at a given point z0. And now we can just split this point into a real and an imaginary part. And as before, we call them x0 and y0 respectively. So, with the reasoning from above, we know that this statement here is equivalent to the statement that the corresponding real function fr from R2 to R2 is totally differentiable at the point x0, y0, and that the Jacobian matrix at the point x0, y0 has the symmetric form from above. So there you see, this is our final connection between both notions of differentiability. And exactly this connection now leads us to the Cauchy-Riemann equations. We simply get another equivalence when we use the fact that the Jacobian matrix has partial derivatives as entries. However, in order to do this, we have to introduce new names for the components of the function fr. That's no problem at all, because we know we just have two components. The first one we simply call u and the second one v. Now, both components depend on the two variables x and y. Therefore, we simply write u of x and y and v of x and y. In other words, here we have two new maps that send R2 to R. So please don't forget, here we just have real functions. Okay, and now we know from the last video that in the top left corner, for example, we find the partial derivative of u with respect to x. And now you see, with the partial derivatives in the Jacobian matrix, we find a connection. And exactly this connection is what we call the Cauchy-Riemann equations. They are just two partial differential equations for u and v. In particular, the first one is simply that du dx is equal to dv dy. So here you see, this equation just represents that we have the same number in the top left corner and in the bottom right corner. Okay, and then you might already see it, the number b here gives us the second equation, which is du dy is equal to minus dv dx. And of course, both equations have to be fulfilled at the given point x0, y0. Okay, now you know that we have these two equivalences to describe complex differentiability at a given point. And of course, then we can extend that to a whole open subset to talk about holomorphic functions. In other words, a holomorphic function has to fulfill the Cauchy-Riemann equations at all the points. Okay, then I think it's good enough for today. Let's talk about examples in the next video. Therefore, I hope I see you there and have a nice day. Bye!